Good morning, sir.
Good morning. Are you getting my voice? Are you getting my voice?
Yes, sir.
Okay. Please post message, class is started. Anyone?
Good morning, sir.
Morning. One minute. Okay. Let us start. So already we have discussed structural elucidation of glucose with all the evidences. Today we are going to discuss about structural elucidation of fructose, right? So coming to structure of fructose, right? Molecular formula of fructose is similar to glucose molecule C6H12O6. Is my display visible? Anyone?
Yes, sir.
Okay. Molecular formula of fructose is similar to glucose formula, that is C6H12O6. Then After getting molecular formula, we go for the what type of functional groups are there, what type of atoms are there, what type of arrangement of atoms are there, how many hydroxyl groups are there. Already we have know that fructose is a carbohydrate which is pentahydroxy, which are having polyhydroxyaldehydes or ketones. Okay. So how many hydroxyl groups are there? What is the functional group? Either it is aldehyde or ketone. To elucidate all those things, we have to perform some reactions. So similar to glucose, fructose when repluxed with acetic anhydride, similar to glucose reaction, fructose on reaction with acetic anhydride, when repluxed with acetic anhydride, it will also give same similar to glucose molecule, it will give pentaacetate product. Pentaacetate product. Okay, that means there are OH groups are there in fructose similar to glucose molecule. So if there are OH groups are there, it reacts with acetic anhydride, CH3CO taken twice O, that is giving pentaacetate molecule, means OCOCH3 group. How many are there? 5. Means one OH group gives one acetate, forms one acetate. It is giving pentaacetate, means there are 5 hydroxyl groups. Okay, it indicates what? It shows or it indicates that fructose contains 5 hydroxyl groups. Okay, coming to next reaction, that is third one, on treatment with hydrogen cyanide, similar to glucose molecule, fructose reacts with hydrogen cyanide and gives addition product which is fructose cyanohydrines. Fructose cyanohydrine. Okay, this property is very characteristic to what? Carbonyl compounds. It shows that the reaction shows that fructose contains carbonyl group. What are the carbonyl groups? Either aldehyde, or it is ketone. Okay. Same way, when fructose treated with hydroxylamine NH2OH forms hydroxylamine again, that indicates carbonyl group. Carbonyl group, it may be, it is hydroxylamine. If carbonyl group is there in the molecule, that reacts with the hydroxylamine by losing water molecule. Okay, then it gives hydroxylamine, which is an oxime. Okay, so again it shows that fructose contains a carbonyl group, right? Now, coming to what type of ketone group is there? Either it is aldehyde or ketone. To know that, when fructose is on oxidation, with nitric acid, concentrated nitric acid, okay, what will happen? Already we have seen in the glucose molecule, fructose with concentrated nitric acid, HNO3, gives a mixture of glycolic acid plus tartaric acid, which are having glycolic acid has 2 carbon atoms, tartaric acid has 4 carbon atoms. Okay. Whenever you see the same reaction with glucose, we are getting acid with same number of carbon atoms. Okay. But in case of fructose, when we treated with oxidized with the concentrated nitric acid, that is giving acids with less number of carbon atoms, you see. Okay. The reaction shows that it indicates formation of carboxylic acids with less number. The functional group present is a ketone. Okay, this is very, very important. Means, unlike glucose, it has a ketonic functional group. In aldehyde, we have seen aldehyde functional group. What is the difference? Molecular formula same. There are 5 hydroxyl groups present in glucose as well as the fructose. Both can react with hydrogen cyanide, gives cyanohydrin. Both can react with hydroxylamine, gives forms oximes. Okay, but on oxidation, they are giving different products. Okay, glucose on oxidation form carboxylic acid with same number of carbon atoms, but in case of fructose, C6H12O6, there are 6 carbon atoms, but we are getting acids with lesser number of carbon atoms, which indicates the functional group present in fructose is a ketone. Okay, right. So the reaction shows that fructose contains ketone functional group. Where it is, that is also very, very important. Where it is, its first carbon, or its second carbon, or its third carbon. Okay, for that, go for other reaction. Okay, fifth one. Cyanohydrin of fructose, cyanohydrin of fructose on hydrolysis followed by reduction with hydrogen iodide. Hydrogen iodide, hydroiodic acid. 2-methyl hexanoic acid. Okay, C6H12O6. It is a fructose molecule. First you treat with hydrogen cyanide, it gives cyanohydride. Then second step, you hydrolyze this H3O plus. In third step, you react with hydrogen iodide, hydroiodic acid. What you will get? 2-methyl hexanoic acid. Hexanoic acid. Hex means there are 6 carbon atoms. 2-methyl means we are getting at second position. Hexanoic acid means COOH. Okay, this is the first carbon, second carbon, third carbon, fourth, fifth, sixth carbon. So we are getting here branch methyl group. That indicates the reaction shows that ketonic group present at second carbon, at carbon 2 or second carbon. Okay, means it is adjacent to one of the terminal carbon atom. Okay, means the ketone group present at second carbon, this is at one terminal, right? So this is the reaction. Coming to next one, fructose on reduction with sodium amalgam gives mixture of sorbitol and mannitol. Sorbitol and mannitol. When these reacted with hydroiodic acid and red phosphorus, yields a mixture of N-hexane and 2-iodohexane. The reaction indicates that 6 carbon atoms are in straight chain. Okay. By observing all these things, we can write the structure of fructose molecule. There are 6 carbon atoms are in straight chain. 1, 2, 3, 4, 5, 6. There is a carbonyl ketonic group at second carbon. When fructose is subjected to acetic anhydride, it gives penta-acetyl product, which is indicating 5 hydroxyl groups present. Those 5 hydroxyl groups at different carbon atoms means I am writing OH here, pentahydroxyl group, OH here, 4 OHs over, then coming to OH here. pentahydroxyl product, right? Then remaining you fill up with hydrogens, hydrogen here, hydrogen here, hydrogen here, no more hydrogen required here, hydrogen here, hydrogen here. Okay. Finally, this is the structure. Sorry. Wait. Structure of fructose, which is pentahydroxy ketone. It is pentahydroxy ketone, right? When we write this molecule in Fischer projection formula, at the top we are getting CH2OH, then C double bond O, remaining 3, 4, 5, 6 carbon CH2OH, OH, 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 HH, HH. Okay. Look at these 3 carbon atoms. They are chiral carbons. Yes or no? Yes. Okay. The orientation of these 3 hydroxyl groups are same side or different. That is very, very important thing. Okay. Means what is the configuration after knowing all the functional groups and other things? We have to look at what is the configuration, means how these 3 hydroxyl groups arranged at 3, 4, 5 carbon atoms. That is very, very important. That shows configuration of fructose. Okay, right? So to know the arrangement of these 3 hydroxyl groups at 3rd, 4th, 5th carbons, right? For that, we have to react fructose molecule to get configuration of fructose. We have to we have to react the fructose molecule with 2,4-dinitrophenyl hydrazine. When you react with fructose with 2,4-dinitrophenyl hydrazine, which gives, it reacts with 3 moles of don't be confused, 3 moles of 2,4-dinitrophenyl hydrazine and gives what? Fructosazone. What it is? Fructosazone. Fructosazone. When you take glucose molecule, glucose also forms with 2,4-dinitrophenyl hydrazine, that is glucosazone. Osazones are forming when you treated glucose and fructose with 2,4-DNP. Okay, 2,4-dinitrophenyl hydrazine. Glucose as well as the fructose both gives osazones, both can form osazones. If it is fructose, that is fructosazone. If it is glucose, glucosazone. Means when you treat fructose with 2,4-DNP, it forms fructosazone, which is having similar structure to the glucosazone, right? Glucosazone. What is glucosazone? You see, I am writing here glucosazone molecule. Sorry. Sixth carbon, fifth, fourth, third, right? For glucosazone, CH2OH, OH here, OH here, H here, H here, H here, OH here. Then this is sixth carbon, fifth carbon, fourth carbon, third carbon. Coming to second carbon, there is a N C double bond. Here there is a carbon, C double bond N, NH, C6H5. Then one more carbon here. This is a second carbon. It is at first carbon again CH double bond N, NH, C6H5. Okay, this is the first carbon. What it is? It is a glucosazone. Structure of glucosazone. So fructose, when treated with 2,4-DNP, giving fructosazone, which is having similar structure to glucosazone. That means fructose has same configuration as glucose at 3, 4, 5. From this reaction, the orientation, the configuration or orientation of these three hydroxyl groups are not like this. Then we write CH2OH, C double bond O. At third carbon, OH is left hand side. At fourth carbon, OH is right hand side. At fifth carbon, OH is right hand side. Okay, sixth carbon, CH2OH. You look at this at 1, 2, 3, 4, 5. At 3, 4, 5, glucose and fructose both are having similar configuration. Okay, from this reaction, we can write the configuration of 3, 4, 5 at carbon atoms 3, 4, 5, right? Which are similar, which is having similar configuration with the glucose molecule. Finally, this is the open chain Fischer structure of fructose. Okay, this is the final, which contains CH2OH group, CH2OH group, but it is it is having ketone functional group. That is the difference. Okay, so this is the configuration of fructose molecule. Now, coming to, there are few reactions similar to glucose molecule. Fructose also doesn't give any reactions. Sorry. So already we have discussed all these things. This is a glycolic acid, CH2OH, COOH, which contains, when fructose oxidized with nitric acid, we are getting 2 carbon atoms acid, which is glycolic acid, 4 carbon atom tartaric acid. Okay. Yeah, you see, fructose when treated with 3 molecules of phenyl hydrazine, then we are getting this osazone at 3, 4, 5 carbon atoms. The configuration of arrangement of OH groups similar to the glucose molecule. These 3, 4, 5 carbon atoms. Okay, glucose and fructose are forming same osazone, which indicates at 3, 4, 5 carbon atoms, arrangement of hydroxyl groups are similar in glucose as well as the fructose molecule. Okay, now finally we conclude that after all the evidences, we can write this structure for the open chain structure of the fructose molecule. Now, similar to glucose, there is a few evidences. It is not having open structures. Okay. Factors against the open structure of fructose means not only it has open structure, but also it has a cyclic structure. What are the factors against to the open structure of fructose? It is very, very important. Okay, like glucose, it does not form like glucose. It does not form addition product with sodium bisulfite, which is weak reagent. Okay, sodium bisulfite, although it contains ketonic group, it contains ketone group. Okay, if it has ketone, it should be react with the sodium bisulfite, but it is not reacting with sodium bisulfite like glucose molecule. It is not giving any addition product. Okay, it is against to the open chain structure. Coming to second one, like glucose, fructose also shows or exhibits. Fructose also exhibits mutarotation. What is mutarotation? Already we have discussed it. Okay, the change in specific rotation without affecting any chemical properties is called mutarotation. Okay, that means fructose also exhibits mutarotation, means it can be exist in two isomeric forms like glucose. We have seen glucose has two isomeric forms. One is alpha glucose, second one is beta glucose, right? So similar way, fructose also exhibits mutarotation. That is shows that it can also be exist in two isomeric forms. Okay, which is against to open chain structure again. Okay, means two isomeric forms means what? Alpha and beta forms, similar to glucose molecule. It also exists in two forms, two isomeric forms, that is alpha and beta. Okay, these two factors are against to the open chain structure. Okay, these two properties can be explained by the ring structure of fructose molecule. Like glucose molecule, fructose also exists in cyclic form. Okay. To get cyclic form, how open chain structure converts into ring form, that is also important. Already we have discussed in glucose ring structure, CHOH, CHOH, CH2OH, right? First carbon, second carbon, third carbon, fourth carbon, fifth carbon. This is the open chain structure of fructose. Open chain structure of fructose, right? So to get cyclic form, this second carbon carbonyl group, 5 electrons shifted over oxygen atom, then carbon gets the positive charge. Now the hydroxyl oxygen of fifth carbon contains lone pair of electrons. This oxygen donates electrons to this carbon, and hydrogen leaves as H plus attached to the oxygen molecule. Then it can be converted into cyclic form CH2OH. Okay. This is the CH2OH. Then this carbon, second carbon, getting what? Already these electrons are shifted over here, then hydrogen comes over here. Okay. Then this O becomes OH. Now this oxygen connected with the second carbon. Third carbon configuration is same as it is OH. Fourth carbon configuration same as it is. Then fifth carbon here, oxygen participates in the cyclic bond with the second carbon. Again, sixth carbon similar. First carbon, second carbon, third carbon, fifth carbon, this, sorry, 1, 2, 3, 4. Fourth carbon, this is the fifth carbon, sixth carbon, right? There is a linkage between C2 and C5 carbons. Okay, C5 oxygen involves bond with the C2 carbon. Mute yourself. Hello. Okay, right? Now you see, this is a cyclic structure of fructose. In a ring, how many atoms are there? You see, 1. This is the first one. 1, 2 oxygen atom second. This carbon, or you count from carbon atom. 1, 2, 3, 4 carbon atoms in the ring and 1 oxygen atom. Means this is 5-membered ring structure. 5-membered. Unlike glucose, 5-membered ring here. In glucose, I have seen that inside ring there are 6 atoms, which is having pyranose structure. What is pyranose? Okay, this is the pyranose structure. Unlike glucose, fructose is having 5-membered ring, which is known as furanose structure. Furanose. This is the furanose. Furan. How many atoms are there? You see, oxygen 1. This is 1, 2, 3, 4, 5. Furanose ring is the 5-membered ring. Pyranose ring is a 6-membered ring. Okay, glucose exists in pyranose structure. Fructose exists in furanose